Let us begin with our chapter 3 on our video lecture series on design of reinforced concrete structures. And today we will start with the design of beams and we will see its behavior in Flexural. So there are three main topics to be discussed in this chapter. The first is the flexural behavior of reinforced concrete. After looking at the behavior of reinforced concrete both theoretically and analytically, we will then proceed with the design of rectangular beams and design of flanged beam sections. So in this flexural behavior, in today's lecture, we will see theoretically how a reinforced concrete structure or how a reinforced concrete beam in particular behaves on the application of flexural force. And in next lecture, we will derive some analytical expressions regarding the behavior. So let's begin with today's lecture. Beams are members that are primarily subjected to flexure or bending. Our beams may also be subjected to some amount of axial force, but that axial force is negligible. The primary force that a beam is subjected to is this flexure or bending. And today we will discuss the behavior of our beam on the application of flexural force. So if we talk about a reinforced concrete beam, let me draw a diagram here. For example, let us suppose that we have a simply supported beam here, which section is represented by this diagram. We have a rectangular beam whose width is B and the total depth is capital D. So if this beam is subjected to a uniformly distributed gravity load, then this beam deflects in similar to this manner here. The dashed line that you see on your screen, this represents the deflected shape, or this represents the elastic curve of our beam. So if you look at the deflected section corresponding to this deflected shape, then what happens is that if you take a section of your beam, then you can find that on the application of this uniformly distributed load, the upper fibers of our beam are subjected to compression, whereas the lower fiber of our beam are subjected to tension. So this uppermost fiber has or is subjected to the maximum compressive force, whereas this lowermost fiber is subjected to the maximum tensile force. So if you take this shape of the beam here, then there is one section, an imaginary section at the middle of the beam or somewhere in the middle, which divides this compressive zone and this tension zone. And this imaginary axis is known as neutral axis. So we will discuss about the position of this neutral axis based on different kinds of reinforced concrete beam in our upcoming lectures. But for today, just remember that this compressive zone and this tension zone is separated by an imaginary axis known as the neutral axis. And this neutral axis is a zone of zero stress. That is, there is no stress acting on this neutral axis. So we generally provide reinforcement in the tension zone. If you see the cross section, suppose that there are three longitudinal bars in this beam, and if this is the neutral axis, we generally provide this reinforcement in the tension zone of our beam because our concrete is weak in tension and these steel reinforcements are needed to resist the tensile forces acting on this beam. So if these reinforcements are only provided in this tension zone, then we call that beam as singly reinforced beam. In such case, you may find some bars in the compression zone also, but these are only known as hanger bars, and these hanger bars are used to tie our beam with the stirrups. Let us not stress on this design or this what stirrup means. Let us just remember that in singly reinforced rectangular beam, there may be some bars in the compression zone also, but they are just used to hold the stirrups together, and these are known as hanger bars. So when reinforcement is only provided in this tensile zone, it is known as singly reinforced rectangular beam. But when the reinforcement is provided in both compression and tension zone, then that type of beam is known as doubly reinforced beam. For example, we have 3 bars here in the tension zone and 3 bars in the compression zone. This is our doubly reinforced beam. So one classification of reinforced concrete beam is in this way. On the basis of where our reinforcements are present, we can classify our RC beams. And another classification of reinforced beams may be based on the type of failure that may occur or based on the precedence of failure that may occur in our reinforced concrete beam. In this classification, we have 3 types: over-reinforced beam, balanced section, and under-reinforced beam. We touched upon this failure a little in our previous lecture, in which we said that we always ensure or we always desire ductile failure. So ductile failure is that failure in which our steel bars yield at first before the failure of concrete. Since concrete is weak in tension and the failure due to crushing of concrete is generally a brittle failure, that type of failure is sudden and there is no warning. So we generally want to ensure that our steel bars fail at first, and that is known as ductile failure. So an over-reinforced beam results in brittle failure of concrete under compression. This brittle failure is sudden and do not give any warning before failure. When the amount of reinforcement required is greater, or when you use that amount of reinforcement which is greater than that required as compared to the compressive capacity of the concrete, then in that case may result in over-reinforced beam, and thus over-reinforced beam when subjected to stresses may result in brittle failure which is sudden and do not give any warning before failure. The second type is the balanced failure, in which both the concrete and steel fail at the same time. And the final type is under-reinforced beam, in which failure is initiated by the yielding of steel. So remember here, in under-reinforced beam, failure is initiated by the failure of steel or yielding of steel, but the final failure may be either due to yielding of steel or concrete compression. The failure is initiated by the yielding of steel, but it is not necessarily that the final failure is also due to yielding of steel, but the final failure may be due to concrete compression also. And this type of failure is ductile, and it gives the users of any structure or user of a building enough warning sign before the final failure, and hence it is known as ductile failure. So this is a general introduction to RC beams. So now we will start with flexural behavior of RC beams, and first we will look at some theoretical concepts regarding the flexural behavior before deriving analytical expressions, which we will do in our next video lecture. So first we will start with uncracked section. The same example is given here as we discussed in our previous slide. We have a simply supported rectangular beam here, which is subjected to a uniformly distributed load of W per meter. It has a length of L, and under the application of this load, this is the deflected shape of our beam. And if you cut a section anywhere in this beam and look at the section, then you see that the topmost fibers are subjected to compressive force, so this is the compression side, and the lowermost fibers of the beam are subjected to tension force. This dashed line here probably represents the position of reinforcement in our beam. These cracks you can see here. So in this slide, when we are discussing about the uncracked section. That means these cracks has not appeared yet. So we know that this uniformly distributed load introduces or induces these internal forces in our beam, which is this moment force here. So under the application of this moment, the beam deflects and such a deflected shape is created. So as long as this moment is small and does not induce cracking, The strains across the cross section are small and the neutral axis is at the centroid of the cross section. So what it means to say that if you see the same section of our rectangular beam here, we have 3 reinforcement bar here. This B is the width of our beam, capital D is the total depth, and small d is the effective depth. We will discuss an effective depth more in our upcoming lectures, but for now effective depth is the distance from this topmost compression fiber or the extreme compression fiber to the centroid of this reinforcement group. So if these are our reinforcement, let us say I have enlarged them, then draw a line through the middle of these bars, then the distance from the topmost compression fiber to this middle line is known as the effective depth or small d. And the distance between this centroid of this bar to this topmost or extreme tension fiber, this we call as cover. So what happens is that when the moment induced in our beams are small, then there is no cracking in our beams. And in such case, when no cracks are developed yet, the strains in our beam is also very small and the neutral axis is at the centroid of the cross section. So now our centroid is at a distance of d by 2. And at this distance of d by 2, our neutral axis also lies here. Our strains are small in this case. So this is the stress diagram and this is the strain diagram. You can see here that when there are no cracks developed, both our stress and strain diagrams are linear in nature, and the linear relationship between force and displacement can be applied here. So we know that modulus of elasticity is given by stress upon strain. Stress upon strain. And if you want to get the value of strain, then you just have to do upon modulus of elasticity. So using this relationship here, you can derive the strain diagram from our stress diagram, since this linear principle or the linear relationship between force and displacement holds here. So the stresses are related to the strains and the deflection is proportional to the load. So in this case, when both the stress and strain behavior are linear, then this Euler-Bernoulli equation applies to our uncracked section. You have derived this equation while studying strength of materials. M represents the moment, I is the second moment of area, F is the stress, Y it is the distance from the neutral axis to that layer where this stress is developed, F. EC is the modulus of elasticity and R is the curvature. So you can rearrange this to get the value of M. M is given by F. If you take this I here, Fi over Y and Fz. So Z is equal to I over Y. In this way you can get the value of this F here, which is given by M over Z. Z is known as the section modulus. And moreover, you can use this equation also. You know that M over EIC you get 1 by R, and this 1 by R, this is the equation of our elastic curve, which is d square y by dx squared. So this relationship can be used for this uncracked section. Similarly, other relationships have also been derived here. You can see we have derived the value of phi, which is our curvature. The value of phi is given by d theta over dx. If you look at the diagram at the bottom here, we have taken a section of our beam where d theta is the small angle subtended by this small radius dx. Hence our curvature is given by d theta by dx or 1 by r. So if you look at this diagram on this right hand side here, using the property of similar triangle, you can find this curvature here. Phi is our curvature. So the value of phi is given by epsilon cu. This is the strain in our concrete under compression. Epsilon cu over, if we say that the distance of the neutral axis from this topmost compression fiber is xu, then for small angle phi, the value of phi is given by epsilon cu over xu. So in this way, different relationship can be derived for uncracked section. You can see here D is the effective depth of the beam, which is discussed in clause 23 of IS 456, and phi is the curvature of the beam, which is also the slope of the strain diagram, as we just saw in this figure here. Now let's look at cracking moment. As we gradually increase the value of the uniformly distributed load that was acting in our previous beam here, the value of this moment that is induced in our beam also increases. So let's see here, as the load is increased, the extreme tension fiber of the beam cracks as the stress reaches the value of modulus of rupture. So if this was our beam here, this lowermost part of our beam, or this extreme tension fibers, which is subjected to tensile force on the application of this load here, these are subjected to certain value of stress, and this C represents the concrete. And as this value of W is increased, the value of M also increases, and as this moment increases, then at one point comes when the cracks start to appear in this extreme tension fiber. And that condition, or that value of stress at which the cracks start to appear in this concrete, that value of stress in concrete is known as modulus of rupture of concrete, or FCR. And the moment that produces the first crack is known as the cracking moment. So the stress in our concrete at the time of this first crack is known as FCR, or modulus of rupture, and the moment that produces this first crack is known as the cracking moment. So at this point of cracking moment also, you can use the relationship that we saw before, M over I equals to F over Y equals to E over R. Now if you want to calculate the cracking moment here, then the value of F, which is stress, you have to use this modulus of rupture FCR. Ig means the second moment of gross area ignoring reinforcement, and Yt is the distance of extreme tension fiber from the neutral axis. So the symbols are the same, except these suffix have been added here, which represent different things here. This is the cracking moment, this is modulus of rupture, this G means the gross second moment of area, and Yt is the distance of extreme tension fiber from the neutral axis. Again, Ig over Yt can be substituted at the section modulus Z. Similarly, you can derive the section curvature at cracking, phi Cr, which is given by mCr over Ec into Ig. So we will, in our upcoming lecture, we will discuss one numerical related to the calculation of this cracking moment in beam. To calculate the cracking moment, this Ig value, or the second moment of gross area, you can calculate by knowing what type of section is used in your beam. The Yt value, which is the distance of extreme tension fiber from the neutral axis, you can calculate from this section itself. But how do you calculate the value of FCR, or this modulus of rupture? The value of modulus of rupture is given in IS code, or IS 456, in this clause 6.2.2, and it says that the value of FCR is dependent on the characteristic strength of concrete that we have used. So the value of FCR is given by this equation here, 0.7 multiplied by the square root of the characteristic strength, and this value is given in Newton per millimeter square. So flexural strength, or this modulus of rupture, is dependent on the characteristic strength of concrete. If we look at the value of FCR in the American code, which is the ACI code, then in ACI code in clause number 19.2.3, the value of modulus of rupture is given as 0.62 lambda root over Fc prime represents the characteristic strength of concrete. Fc prime and Fck means the same, only the notations are different, and lambda, it has a separate some sort of modification factor for lightweight concrete, which we do not have in our IS code. So you can use this clause in IS code to calculate the value of FCR and hence to calculate the value of cracking moment. So here we have discussed the condition at which the cracks have just started in the tension side of our beam. And finally, we will look at the cracked section. So what happens is that the cracks first start to appear at the extreme tensile fibers or extreme fibers in the tension zone. And gradually, these cracks start to propagate towards the neutral axis. So the cracks widen and propagate gradually towards the neutral axis. The cracked portion of the concrete beam is ineffective in resisting the tensile stresses. So whatever small capacity or small tensile capacity our concrete beam has, as these cracks appear, that small tensile capacity is also ineffective now. That tensile capacity vanishes. And what happens is, at one point, the steel reinforcements come into play as these cracks widen and become bigger and propagate towards the neutral axis. The steel reinforcements come into play and there is a sudden transfer of tension force from the concrete to the reinforcements in the tension zone. There is a sudden transfer of our tensile forces from this concrete in tension zone to the reinforcements in our tension zone. There is an upward shifting of the neutral axis. We will look in detail about this position, the depth of our neutral axis when we derive the analytical expression for the flexural behavior. But just remember that as the cracks widen, as the cracks propagate towards the neutral axis also shifts in position and there is an increased curvature at the cracked section. So if you see at this figure here, for the uncracked section, both our strength and stress diagrams are linear. And at one point, it comes where now cracks start to appear at the tension zone, or cracks start to appear at this bottommost layer of our concrete. And you can see this dashed line here. This dashed line represents that now the concrete in this tension zone is ineffective and the whole of these tensile forces are now transferred to the steel reinforcement, which is represented as Fs. This is the tension stress, or this is the stress that is present in this reinforcement steel bars. So dashed line represents the ineffective concrete, the concrete that is ineffective in resisting the tensile forces here. And finally, as the cracks widen, as the cracks propagate towards the neutral axis, this linear stress, this is the strain diagram. Now this linear stress diagram now changes into a different non-linear shape. So we will discuss about this. This is known as the stress block. We will discuss about the shape of this stress block and how this shape follows the stress-strain diagram of concrete that we discussed in our previous lecture. We will see about all of this in our next class or next section. So this is about the cracked section. What happens when the cracks start to appear and they start moving gradually towards the neutral axis. So finally, what happens? If the loads are increased further, the tensile stress in the reinforcement and the compression stress in the concrete increases further. So now, the concrete in the compression zone resists our compressive forces and the steel in the tension zone resists our tensile stresses. And as we increase the load, the compressive stress value also increases and the tensile stress value also increases. Both these value of these stresses increase. The stresses over the compression zone will become non-linear as we saw in our previous diagram. If this was our stress diagram at one point, when this concrete in the compression zone was resisting our compressive forces and the steel in the tension zone was resisting our tensile stresses, this is our linear stress diagram, and as the load is increased, now this changes to non-linear shape. The strain distribution over the cross section, however, remains linear. This is from our assumption of plane section remain plane after bending. Now this is called the ultimate stage. So once we have reached the ultimate stage, once these strain values in our concrete and steel have reached the ultimate values, now the failure occurs in our beam. So failure may occur in two ways, as we discussed in our first slide of this lecture. If our section is a under reinforced section, the steel will yield first before the concrete fails, giving sufficient warning before failure. But if our section is over reinforced, the steel will not yield, and hence the concrete in the compression zone will cross and the beam will collapse rather explosively, suddenly, without giving any warning. So the failure may occur in either of these two ways. We may have a balanced failure also, but having a balanced section is rare. We are not always concerned with adopting or designing a balanced section, rather we always tend to design under reinforced section. So let's say that the failure can occur in either of two ways. When it is an under reinforced section, there will be a brittle failure. There will be a ductile failure, and if our section is over reinforced, there will be brittle failure. So this is about the flexural behavior of reinforced concrete. Okay, before ending today's lecture, let me again repeat this topic which I have repeatedly discussed in our various lectures, analysis versus design. But in this slide, we will look at specifically this analysis versus design of a reinforced concrete beam. So we deal with two types of problems in this chapter, chapter 3. We are either given to analyze RC beam or we have to design. So analysis means you are given the cross section, that means the breadth and the depth. You are given the material properties, for example, the concrete strength. In case of concrete, you are given the characteristic strength, and in case of steel, you are given the yield strength. So these are the material properties which are given for analysis. And finally, you are given reinforcement size and location. And what you have to calculate is you have to calculate the resistance or strength of your beam. And this is in analysis portion. Whereas in design, you are only given the factored design moment that is acting on your beam, and you have to determine these various things: cross section, concrete strength, reinforcement. So this is exactly opposite. Whatever is given in analysis, you have to find in design, whereas whatever you have computed in analysis is given in your design. So in analysis, there should be one unique answer. If you are given all these things, then the resistance or strength of your RC beam section should be unique. There can be only one value. But if it is design, then you can have many different possible solutions. For example, based on the type of cross section you choose, the amount of reinforcement may vary, or based on the strength of concrete that you employ in your RCC beam, the amount of reinforcement and the cross section both may vary. In this way, the final design results may vary according to the designer. So this is the difference between analysis and design. So I would like to end here today. In our next lecture, we will begin with deriving the analytical expressions. And first, we will look at calculating this design bending moment capacity of rectangular beams. That means we will see how to calculate the bending moment capacity of rectangular beams for different given data such as the concrete strength, the amount of reinforcement, or the dimensions of your RC beam, etc. So we will start with this slide in our next class. Till then, stay safe. Before next class, before beginning with this slide, in our next class, we will see a numerical relating to the design of, relating to the calculation of cracking moment, and then only after that class, we will start with this design bending moment capacity of rectangular section. So till then, stay safe and thank you.